And so good morning, everyone, for our June 28th ME316 live lecture. Where we finished off last week was concluding Chapter 7 material, and then also just explaining that Chapter 11 was really just the combination of Chapter 6 and 7, designing a beam, taking into account both the effects of bending and transverse shear. And so we have that homework that's due this Saturday, and then the first exam due next Tuesday. And we have the 4th of July weekend coming up, so you can kind of plan your schedule accordingly. Maybe you can get done with stuff before the 4th of July weekend so you don't have to worry about any of that stuff. Let's see. The homework that you submitted this past Saturday on torsion, my plan is to get through the grading of that by tomorrow so that I can get those scores posted and then the solutions posted as well. That way, if you have any questions over the torsion content for that first exam related to the homework, you'll have time to do that on Wednesday or Friday this week. I'm not sure how the holiday schedule works with the 4th being on a Sunday, but unless I hear otherwise, I'm planning for the full week. And so we'll go ahead and get started now. I'll share my screen. And from Hibbler's textbook, we did chapter 6 and 7, and then jump forward to chapter 11, where it's the combination of bending and transverse shear. And it works out well to continue on to chapter 12 that focuses on the deflection of beams and shafts. Before we head back earlier to discuss combined loadings. This all kind of content fits really well together, just to combine all the beam information into one unit, really for our second exam that'll be in July. So chapter 12 focuses on the deflections of beams and shafts, and it's similar to what we did with axial loading, where we looked at the axial deflections. Similar to torsion, where we looked at the angle of twist that developed, and now we're just doing the same thing for beams, looking at the deflections that occur within a beam. And so this kind of takes us through the details of that. It does get a little bit heavy into the calculus with integrating back a number of times, having your constants of integration, and solving those constants of integrations with your boundary conditions. And so as we start out today, I'm just going to take you through that whole process, essentially with a distributed load. And then as we continue on into the week, we'll learn more about continuity and things like that to help solve those types of problems. But we can start first just by considering a simply supported beam with a distributed load W. And it's of length L. And so some things to be aware of is that your slope theta is just equal to the derivative of the vertical displacement with respect to X. And so there's oftentimes constraints on both the displacement V and the slope theta in relation to the boundary conditions that you're going to be using. And again, typically the axial direction is located along the X direction and Y vertically upward. Although when you look at the cross-sectional properties, they tend to put that on the XY plane too. It should technically be the YZ plane. We talked about that last week. but that deformed shape that the beam will take is defined as the elastic curve, and it just represents that deflected shape of the beam. And in terms of the deflections, if you look at the x direction, deflections in the x direction are defined by u of x, which is just deflection in the x direction. In the y direction, it's v of x. It's the deflection in the vertical direction or the y direction. And z is w of x, deflection in the z direction. And so this gets confusing when you start looking at, say, Roark's formulas for stress and strain, and they're doing full 3D bending for plates and shells. They'll use the UV and W as the vertical deflection. And so this is not related to the distributed load at all. And so that's just something to be aware of if you ever are looking at Roark's formulas for stress and strain, that their WX terms in there are typically going to represent that deflection in the Z direction. But just look at the context of how those expressions are being posed. For bending like this, we are only really concerned with the deflection in the y direction, so the V of x term. So I have a box around that. And then for everything that we're doing in Hibbeler, that W that we're going to look at is going to refer to the distributed load only here in chapter 12 and within our notes. And so we will not be looking at, say, deflections in the Z direction like you would see in Roark's for formula for stress and strain. And so W is always going to refer to that distributed load. But in general, we have our positive definitions for free body diagram, deflection and slope. You can remember that from our positive notation on beams, the internal shear and moment. Remember, on the right-hand side, the shear is positive down, moment positive counterclockwise. On the right-hand side, moment positive clockwise, shear positive upward. And the new definition, the distributed load is positive when it's in a vertical direction. And so that's the positive definitions for the loading that occurs within a beam. And then for the vertical displacement as a function of x, again, this is for situations where the x-axis is defined positive to the right. If the slope is going downward to the left, that's a negative slope. If it's going upward to the right, it's a positive slope. And then positive deflections are in the positive direction, negative deflections are down. And then we have a positive radius of curvature as well. If it makes a bowl shape, that's going to be a positive radius of curvature. It gets confusing. Some of these switch around if you have x going positive to the left. So I just tend to always make x positive to the right in the free body diagram, so then you don't have to worry about those issues at all. And then from chapter 6 for beam bending, you have sigma x is equal to minus E over rho times y, where y is that position with respect to the neutral axis of the beam. And we then looked at already for bending that sigma x is going to be a minus my over I. And so we can state that is equal to minus E over rho times y, and our y's will cancel, our negative signs will cancel, and we'll be left with a 1 over rho for our radius of curvature is equal to m over EI. And so rho again is our radius of curvature. 1 over row then defines the curvature of the beam. And if you look in that front cover of your Hibbeler Dynamics textbook, do you still have your Hibbeler Dynamics textbook, Jordan?
Yes, I do. I think it's downstairs.
Okay, and so take a peek at that. They will define your radius of curvature for you in this manner, where that is then equal to 1 plus dv dx squared, quantity to the 3/2 power over d squared v dx squared. And that's my go-to source whenever looking at the radius of curvature. That shows up nicely in your Hibbeler textbook for dynamics. And typically with beams, we really don't want those to deflect large distances. And so deflections are going to be small. If you think about bridges, buildings, things like that, bad things happen when deflections become really large. And so we're looking at small deflections. And so the dv dx will be small in that regard. And so the squared of a really small number is approximately 0. And so this term inside here, dv dx squared, will be approximately 0. So you're left with 1 to the 3/2 power. 1 to any power is still 1. So we're then left with d squared v dx squared is equal to m over ei. And I was always under the mindset that for small deflections, this would then only work for about deflections on the order of the thickness of the beam. If you go greater than that, it's going to deviate widely. But we have done experiments for ME110 and ME316 in the past, where we have found that we've gotten significant displacements out, and it's still followed that generally well from a linear perspective, where you could calculate the Young's modulus of the material that you're bending. But in general, you're going to have constraints on how much a system can displace. So that's generally not a concern. And so if we rearrange this and solve, and this is going to be an internal moment as a function of x, is equal to ei d squared v dx squared, assuming that e and I are constant. And that really puts us kind of square in the middle of how all of these items are related to one another, where a moment m is equal to ei d squared v dx squared. We looked at that in the past, where we said when we're looking at shear moment diagrams that the internal shear is equal to dm dx and the distributed load is equal to dv dx. And so we can follow that path down pretty easily. For internal shear, if we just take the derivative of moment with respect to x, we'll just end up with an ei d cubed v dx cubed. And if we take the derivative again with respect to x, we'll get the distributed load is equal to ei d to the 4th v dx to the 4th. And then if we look at that, we have in this expression the approximation for the curvature, d squared v dx squared. But if we integrate that term back, we'll end up with the slope, which is dv dx theta. And if we integrate back again, that'll give us our deflection v. And so we really have these 5 relationships that kind of tie the distributed load through to deflection. And there's a couple ways that you can generally solve this. The rare instances where you have, say, a distributed load acting on something and you're all down at this level and you integrate back 4 times, arriving at 4 constants of integration. and then being able to solve from that standpoint. That's kind of a rare occurrence. More commonly, what we'll be doing is relying on what we learned in chapter 6 and 7 to look at what is our internal moment as a function of x. And then with that, we can integrate back twice and solve our two constants of integration. And so we'll do both of those. Today, we'll look at the case primarily with the distributed load, integrating back 4 times. And then we'll do one example with the moment and continue on with that as we move forward into the week. But this was something that I don't remember touching on that greatly. And so it kind of helped me make these notes to really show that process. And before going on looking at moments as a function of x. But again, we need to integrate these while solving for the constants of integration with boundary conditions and continuity. And in chapter 12, they refer to it as continuity, but it's just another fancy name for compatibility that we looked at already when talking about indeterminate type of problems. And so let's just take that first example of a simply supported beam, direction XY axis, and a distributed load acting downward on that beam. It's just going to cause it to deflect downward in a symmetric style. Distributed load W is acting down, so that's a negative distributed load. And so we really start at this level and then integrate back. And so we have EI d to the fourth v dx to the fourth is equal to a minus W as our first equation. And then if we integrate back, I'm just doing integration fairly quickly here. We'll end up with the cube terms equal to our shear force. And when we integrate that with respect to x, we end up with a minus Wx plus C1. Since W is a constant, it was not a function of x at all. So it just ends up with a minus Wx plus C1. So just doing indefinite integrals at this point. Give us our second equation, integrate back again. We have EI d squared v dx squared is equal to our moment. So this is our internal moment as a function of x now. And that's going to be a minus Wx squared over 2 plus C1x plus C2 will give us our third equation. Integrate back again. We minus Wx squared over 6 plus C1x squared over 2 plus C2x plus C3. And then integrate back one more time. EIV is equal to minus Wx to the fourth over 24 plus C1x cubed over 6 plus C2x squared over 2 plus C3x plus C4 will give us our fifth equation. And so these really are our 5 governing equations for our simply supported beam with a distributed load. And now at this point, it's really just a matter of applying boundary conditions to determine what our 4 constants are: C1, C2, C3, and C4. And when you're doing this, it is kind of helpful to see what is 0, what displacements and slopes are equal to 0. And can I put those in there to just eliminate constants right off the bat? And so what we're kind of referring to when we look at boundary conditions, we know that at x equal to 0, the displacement is going to be equal to 0, And at x equal to L, the displacement is going to be equal to 0. Additionally, we know that the slope is going to be 0 at the center of the beam because that's symmetric. And these supports are not able to provide any resistance to a moment. So the moment's going to be 0 at the left and the right hand side as well. And so for this one, the boundary conditions are going to eliminate quite a few things. But we know that V is going to be 0 at L equal to 0. So V is 0 is equal to 0. And what happens there is all your X terms, where there's an X term, that's going to be a 0 value. Our displacement's 0 at that point. So we have all these zeros. 0 is equal to 0 plus C4. And so the only way that's going to happen is if C4 is also equal to 0 from equation 5. And so that's applying one boundary condition will eliminate C4. And we know that the moment of x equal to 0 is equal to 0. And so if we plug that into equation 3, again, 0 on the left-hand side, all these are zeros, plugging in x equal to 0 there. So we know that C2 is equal to 0. So we got rid of another constant of integration. And then we know that the moment at L is equal to 0. Kind of why I did this one first. We know V of L is equal to 0. But if we were to plug that in, C2 and C4 are 0 already. But C1 and C3 are unknown at that point. So if we were to plug VL equal to 0 at this point, we'd have one equation and still two unknowns, C1 and C3. And so instead, if we use the M of L equal to 0, C2 has already been taken out. And so we can solve for C1 directly there. And so when you're looking at these 5 equations, kind of pick boundary conditions where you end up with one equation, one unknown as you're going along. And that'll kind of help you out in that process of solving your constants of integration. And so ML equal to 0. So the left-hand side 0, x equal to L. So we'd have a minus WL squared over 2 plus C1 times L, and C2 is 0. So we just end up with those two terms. And then we can solve for C1, move that to the other side, and divide through by L. We'd end up with C1 is equal to a WL divided by 2. And so we know now what C1 is that would be required to get the moment at L equal to 0. Then we can move on to equation 5 and V of L equal to 0. I'm going to slide that back up so we can see everything. And so we have 0 on the left-hand side. Plugging in L, we have minus WL to the 4th over 24 plus C1, which is a WL over 2 times 6 will give us 12. And then we have the L times an L cubed, which will give us an L to the 4th. So all we're doing is plugging in WL over 2 times L cubed over 6 will give us WL to the 4th over 12 plus C3 times L. So again, we have one equation, one unknown, where we can solve for our C3 constant of integration. Just doing the algebra on that, we end up with a minus WL cubed over 24. And so we then end up with our two constants of integration that are non-zero, C1 being WL over 2, and C3 being minus WL cubed over 24. When we plug those constants of integration back in for equation 5, then we'll end up with EIV time or is equal to a minus WX to the 4th over 24 plus C1. We plug in C1 there. WL over 2 times x cubed over 6 will give us a WL x cubed over 12. WLX cubed over 12. And then C2 0 and C3 is just C3 times x. So minus WL cubed over 24 times x. And this then gives us the fundamental expression for our elastic curve. And then we have to be careful. We have this Young's modulus and area moment of inertia dangling out here on the left-hand side. So generally you move that around to the right-hand side and just express your elastic curve as the V, the displacement in the Y direction, as a function of X. And so that's going to be equal to a minus WX. I can pull an X out of all these. I can pull a 24 out, and then EI got divided through by both sides. And then we'll be left with an x cubed minus a 2lx squared plus an L cubed when we simplify that down. And so that is then the elastic curve. And note that, again, the slope at L over 2 is also equal to 0. So what you'll find is you may have more conditions that you're aware of that you could use to solve for your constants of integration, but they're not necessary, as we were able to solve those just based on the displacements at x equal to 0, x equal to L, and the internal moment at x equal to 0, x equal to L. But these then serve as a great way to verify your solution. If we know this is the case, we can plug that through and verify that is the case, that the displacement's equal to 0. And so we can plug that in. We have our displacement as a function of x. And so we could just solve now for the slope equal to dv dx. And doing that, it's a little bit easier to move your x back into the relationship there. I did that right here, moved the x back in. So it's x to the 4th minus 2l x cubed plus l cubed x. Otherwise, you have to do the product rule as you're doing your derivatives. So that becomes a little bit more of a headache. So if you're ever doing the slope, just bring any x values back in. Then if we take the derivative of that, this is all a constant out in the front. And so we end up with a 4x cubed minus a 6lx squared plus an L cubed. And if we plug in then theta at L over 2, we'll end up with a 4L cubed over 8 minus 6L cubed over 4 plus an L cubed. And then we'll have 4 8s altogether. L cubed minus then a 12 L cubed over 8, getting common denominators there. And 4 minus 12 is a negative 8 L cubed over 8 plus L cubed. And so that's just minus L cubed plus L cubed, which will be 0. And so we just confirmed that indeed the slope at L over 2 is equal to 0 to satisfy the symmetry of this problem. The other thing you're probably just beginning to understand here is that we're doing a lot of calculus and algebra with letters and not numbers. This is a really useful tool because then for this particular case, Instead of just solving it for one problem, you now have an expression that you have the elastic curve for any type of beam simply supported that has a distributed load on it. You just have to plug now in the parameters of the length of the beam, the Young's modulus, the area moment of inertia, what is the distributed load acting on it, and presto, you have your expression then for your displacement as a function of x.
And this is only if W is constant, right?
Correct. Yep. This is only if W is constant. If you have a W that's varying with respect to X, that would show up all the way back here. Instead of putting in like minus W, it would be whatever your distributed load is as a function of X. And then you could integrate that through. But more likely than doing it in that manner, you would more likely then figure out what is the internal moment as a function of X and start out at this level for equation 3 here. This is where you would start, and then you would just integrate back twice to end up with 2 constants of integration. Oh, let's see. I kind of wanted to share something too. A lot of these elastic curves are shown then in your appendices as well. And so we'll do a little sidebar. And we have a simply supported beam with a load in the center, a load off center, a moment at one end, and they're all going to give you then what your elastic curve is as a function of X. They've went through that process and derived that out for you. There's also some nice things that they'll do. They'll solve out what is your maximum deflection. This is symmetric, so that would occur at the center of the beam. The max deflection here would occur at X equal to A. And that may not necessarily be the maximum deflection. That's just finding out what is the deflection at point A. How would you go about figuring out what the maximum deflection is?
Wouldn't we need to find the spot under where the point load is on the beam?
Right. If you're uncertain of where the maximum deflection is, you can always solve the slope of the beam and determine where the slope is equal to 0. And that'll give you the X value where the maximum deflection is. And so that's a handy trick because it's not always apparent. Hold on just a second. Sorry about that. But you have a few different cases there. And then when we get down to the second slide, we do see the distributed load on a simply supported beam. And I'll try to bring this up so we can compare and contrast. It says top line here. I'm not sure if I got it into the same form. Okay, yep. So I did get this into the same form that it shows up in the back of the book. V is equal to a minus WX over 24 EI, X cubed minus 2LX squared plus L cubed. And for that, we know Vmax is equal to minus 5 WL to the fourth over 384 EI. That could be solved by placing X equal to L over 2 into this expression and simplifying. And the maximum slope that would occur at the left and the right edges. The left-hand side would be a negative value, minus WL cubed over 24 EI. And that would make that a positive WL cubed over 24 EI on the right-hand side, sloping upward to the right. And so the tables that you have in the back of your textbook really only provide the elastic curve. As we continue on, I'll give you Shigley's tables, which give you more information on the reaction forces, the moment as a function of X. Remember, when you have the elastic curve, you can really solve for all this stuff. It's a lot easier when you have the elastic curve to take your derivatives moving forward. So remember, slope is equal to dv dx, and then moment d squared v dx squared times EI. And so you can get that a lot easier once this is already solved out for you. But I'll give you some more tables that you don't have to do that. That part's already done for you as well. Anytime you're solving problems, as an engineer, you should be able to derive all these things that you find in the tables. But if you're going through the application of designing a beam, if you have a table that has the values already derived out for you, you should be able to use those to solve that problem a lot quicker, because a lot of this work's already been done for you. And so we'll do both. We'll do both derivations to derive that elastic curve, and then we'll also make use of the tables to solve problems more quickly. And the one thing to find out when you're going through and deriving some of these problems, where you need to know your shear moment diagram, your moment as a function of X, and then integrate back twice. When you're deriving that out without using tables, those problems can take an hour to solve. And there's not really just any easy way around that. It just takes time going through the integrations and the solving your boundary conditions and doing all that stuff. Whereas if you have a problem where you can make use of the tables, you can generally do that problem a lot quicker, sometimes in under 10 minutes. If it gets complicated with superposition, there's still going to be algebra involved, but you're probably looking at a half hour instead of over an hour if you're deriving that from scratch. And so this first problem, again, we had a distributed load with a simply supported beam, and we ended up with our governing equations. The interesting thing about these governing equations is that we didn't need any information on the boundary conditions to develop these general equations. We only used the boundary conditions to solve for the constants of integration. And so when we go to our second example, we can see what happens when all we do is we change the boundary conditions. We have a fixed support on the left and free on the right. What we find is that we have the same governing equations, but now different boundary conditions. And so with that, we just have to make use of our boundary conditions for the second example and solve our new constants of integration based on these boundary conditions. And so I'm going to bring up another view of that so we can look at the governing equations side by side as we're going through and doing this. So many windows. Oh. Okay, I was just making sure we didn't have equation numbers off there. All right, I think we're set. And so when we look at these boundary conditions in relation to our 5 governing equations, we know that both the displacement and the slope are 0 at x equal to 0. And then at the free end of the beam, there's not going to be any internal shear moment remaining at x equal to L. And so again, the easier ones to use first are v of 0 is equal to 0. That goes into equation 5. Everything on the left is 0. Everything on the right is 0 except for C4, which means that for that to be 0, C4 has to be 0. Same thing with equation 4. If the slope dv dx is equal to 0, everything else is 0 except for C3. That means C3 has to be equal to 0. And so we knocked off C4 and C3 just with those 2 boundary conditions. And so we're left with C1 and C2. And so when we look at that, we know that V of L is equal to 0 and M of L is equal to 0. If we were to do the M of L equal to 0 first, we'd have 2 constants unknown, C1 and C2. So it makes more sense to go up to equation 2 and put V of L equal to 0 in, because now we only have 1 constant of integration. So we're always looking for that boundary condition that's going to allow you to solve the one equation, one unknown, and then feed that forward into the next one. So V of L is equal to 0. So we have minus WL plus C1, which means C1 is equal to WL. Boundary condition 1 solved, and then M of L is equal to 0. So plugging L in for X, we solved C1 already, we can solve for C2. So we have 0 is equal to a minus WL squared over 2 plus C1 times L, which will be WL squared now, because we have C1 times X, where X equal to L, plus C2. And so C2 is equal to then WL squared over 2 minus WL, which is the same as 2 over 2. 1 minus 2 will give us a minus half WL squared. So minus WL squared over 2. But you can kind of see that went really quick with solving those constants of integration for this particular case after we'd already done our governing equations. And so our elastic curve then is just plugging in our constants of integration. We'll have a minus Wx to the 4th over 24. Plugging our constants of integration in, we'll end up with a WL x cubed over 6. And we're plugging in for C1. C1 was WL, I remember. And then plus C2 which was a minus WL squared over 2. And so that becomes minus WL squared times X squared over 2. When you have the 2 times 2 will give you 4 on the denominator there. And so same thing, always remember you have that dangling EI out there that you have to divide through by. And so your displacement, your elastic curve will be minus WX squared over 24 EI times the quantity X squared minus 4LX plus 6L squared. I think I can get rid of this one now. Bring back up the PowerPoint that I took down already. And so as you go through here, we found on the 4th slide there, the elastic curve for this distributed load on a fixed free beam. Again, I don't know if I've been saying that, but this is known as a cantilevered beam. And so just making that comparison, minus WX squared over 24 EI times the quantity X squared minus 4LX plus 6L squared, just showing that we were able to derive that elastic curve that shows up in the appendix. And again, remember, if you're only given the elastic curve, remember theta is equal to dV dx, and m is equal to EI d squared v dx squared for that case. And so if we're solving for the derivative, I wanted to bring that so you can see it. Again, bring the x squared term back in. So we have minus w over 24 EI times x to the 4th minus 4LX squared, or x cubed, plus a 6L squared x squared. That makes it easier to do your derivative to solve for your slope. Minus w over 24 EI. That would give you derivative with respect to x, 4x cubed minus 12LX squared plus 12L squared x. Taking derivative with respect to x. And then if we take the derivative again, that would be m over EI times d squared v dx squared. Will give you a minus w over 24 EI. And then taking the derivative of these again, we end up with a 12x squared minus 24LX plus 12L squared. And the main thing to remember once you get down to this level is you still have this EI in the denominator on both sides. So EI is going to disappear. So that internal moment is equal to minus w over 24 times 12x squared minus 24LX plus 12L squared. And so that's something that I've seen students commonly forget, that is getting rid of that EI term since they cancel on both sides. But when we're going through looking at our shear and moment diagrams, those were just based on the loadings. The internal shear and moment were not dependent upon the Young's modulus and area moment of inertia. So we see that same thing come through here as we go through the system of equations. And all we did for this was just divide through by E of I on both sides. So m over EI is equal to d squared v dx squared. All right. I think we're going to finish a little bit early today in the second half of the hour. I guess, Jordan, do you have any questions over this first part of the discussion on beam deflections?
I don't think so. Everything seems all right. We'll see how it goes once that load turns into something that has an equation behind it.
Yeah, and it's not, it doesn't make things that complicated because you're generally in that situation going to be solving for the internal moment as a function of x as we did in chapter 6, and then just integrating back twice instead of going through all of these. I think it would be a rare situation where you would start out at the distributed load level as a function of x. There could be some instances like a triangular load type deal, but we'll not worry about that right now.
Okay.
We'll
I'm
look at the,
just thinking back to ME 216, and Dr. Romke's really liked giving us problems with a distributed load that is functionally dependent on the length of the beam and an initial load. I remember doing some really nasty calculus problems last semester.
yeah, it can get kind of messy. It will get a little messy here, but when we are able to bring these back to find the internal moment as a function of x, then it's a little bit clearer because then you are able to then solve for your two constants of integration. So we'll tackle it from that standpoint. Any other questions?
Nope.
I'm going to stop sharing for a second. And so I think now is a good time to take a break and maybe start back up at 10 a.m. And so I'll go ahead and stop